the next thing I want you to be able to do is to be able to look at some different examples of things that you might run across in everyday life and be able to tell, is it in equilibrium, static or dynamic, or is it in accelerated motion? To be able to tell if the forces are balanced or unbalanced, and then also be able to identify the forces. So let's take a real simple example to start with here of, say, just maybe a rock sitting on the ground. Alright, so we got a rock here, rock on the ground. Alright, so you observe the rock and you see the rock is not moving, so you know the velocity is 0. You also know that the acceleration is 0. So based on that, we match that up. That is something that is in static equilibrium. Static equilibrium, and the forces are balanced. So you can tell that just by looking at the motion of the rock. Now, the last thing you want to do here is then actually identify the forces that are acting on the rock. The most obvious one is that gravity is pulling down on the rock, or the weight of the rock, we can call it that. Right, the weight of the rock pulling down. Now, the next one is, if the rock is pushing down then on the ground, third law says the ground should be pushing back up on the rock. And so that's the ground on the rock. And we know those two forces should be drawn about the same length in opposite directions because they're balanced. Another name for this force, the ground force pushing up on the rock, this is a support force. Support force, and we call it a normal force because it acts 90 degrees to the surface. The normal force, right? The angle is 90 degrees in here, right, with the surface right there. So this is called a normal force. So we'll typically, on most things sitting on the ground, we'll have the gravity pulling down on its weight, and then we'll have a normal force that pushes back up on it. Let's take a look at a different one here. Let's take a look at a hockey puck. Promise that's a hockey puck. Alright, and let's have it sliding to the right with a constant velocity. So constant velocity sliding to the right, and let's say it's on frictionless ice. Ice isn't completely frictionless, but we'll just call it frictionless for right now. So the puck's moving along to the right with a constant velocity. So based on that observation, constant velocity, we know it has some velocity, but if it's constant, that means the acceleration is 0. So again, we look back up here, we have velocity here, and we have 0 acceleration. So this is going to be dynamic equilibrium. So let's look at the forces. We're going to have the weight of the puck, right? Gravity pulling down on it, weight, and we have that normal force of the ice pushing up on it. And again, those are balanced. Dynamic equilibrium is balanced, and that's it. There are no side-to-side forces, right? First law tells us that an object in motion will just continue in motion with no net forces or balanced forces acting on it. So no forces is definitely balanced, or a net force of 0. So it's sliding. Now, something had to get it going at some point, but that's not the scenario we're looking at. We're just looking at it as it was sliding with a constant velocity. Next, let's look at an example of a car. Here, and we'll have it along the road and have it with a constant velocity to the right. If it has a constant velocity, then the acceleration must be 0. So we have a velocity, we have zero acceleration. This is going to be, again, dynamic, equilibrium, balanced forces. So if we want to look at the forces, again, we come back to the weight, pulling on it. We have the normal force of the ground pushing up on the car. So that's going to be the road pushing up on it. And we know, just from experience, you know that if the car was just to stop running its engine and everything, left to coast, it would eventually stop. And we know that's because we'd have friction pushing back against it this way. Right, it's going to oppose the motion. And so if we had some friction here, like that. So this is a situation where it helps. We know what's going on. We know there's no acceleration. We know it's dynamic equilibrium, so we know the forces are balanced. And so vertically everything is balanced, but we only have one force here, and that's friction pushing back. If that was the case, then it should be unbalanced towards the left, which would mean to accelerate to the left, which is what causes it to slow down then if it's moving to the right. So there has to be some other force, some other force going the other direction, say some push that's going on here in order to cause this to be balanced out. So the car engine running causes the wheels to turn. The wheels then push against the ground. And according to third law, if the wheels push against the ground, then the ground pushes against the car. And this is different than the road support force. It's different than the normal force. This is a result of the wheel here. So if we look at the wheel up close, right, we look at the wheel right here in contact with the ground, as it's turning, alright, as it's going around, it's going to push against the ground back this way. So the wheel pushes the ground that way. And then the reaction force to that is that the ground pushes back on the wheel like that. And so that's the push that the car has to balance out the friction so they can continue to move at a constant velocity. Alright, let's look at one more here to finish this up. Let's take a look at, say here we have a little round table. We'll look at this from above to start with. And you have a little child running around the table. Alright, so the child is running around the table here, and she's running with a constant speed as she goes around the table. Now be careful here. We said the constant speed. That means maybe going at a continuous 2 meters per second. But that's not a constant velocity, because as you can see, she's going in a circle as she goes around the table, so she's turning. So there's a change in direction. There's a turning that's taking place, which means she is accelerating. Right? So there's an acceleration going on here. So this is going to be accelerated motion. So we want to identify that, accelerated motion. And accelerated motion means the forces are unbalanced, acting on the child here. And so if we kind of look at her separate here again, we can look at the forces vertically. She has weight, right? So she has that force pulling down on her, and she's standing on the ground, right? So there's the ground force, so that normal force is pushing back up on her. Now in order for her to go around in a circle, there has to be some force that causes her. If she didn't have that force acting, if she was just to run along, she could run along straight in that direction, just cruise along there. But in order to turn, there has to be some force applied to her, some kind of force to cause her to go in that circle, to cause her to accelerate in that direction so that she'll turn. And so there's a force, and it's very similar to the wheel pushing the ground, except now it's her feet. Her feet push against the ground like the wheel did, and therefore the ground pushes against her. So there should be a force, right, of the push of the ground like that. And so that force is unbalanced in the sideways direction, which is what causes her then to turn and go around in this circle right here. Alright, so you should be able to take these examples and do the same thing with anything that you run across to identify whether or not something's accelerating or not. If it's not accelerating, then the forces are balanced, you have equilibrium. If it's moving, it's dynamic equilibrium. If you have something that is accelerating, then you have accelerated motion and you've got unbalanced forces. And this allows you to also kind of go through and identify all those forces as well.